now that we know how to assign molecules into point groups, we're going to talk about why we're doing this and how it's going to help us. So once we assign a molecule to a point group, you're going to be able to look at the character table of that point group and see all of the symmetry operations and a whole bunch of other information. So I handed out to each of you 3 different pieces of paper. One of them was the first page of character tables in your textbook. So it's actually page 801 of your textbook. And those are character tables for a couple of the C and B groups, and then some of the other ones below it. So that's what a character table looks like. Once you assign something to a character table, you can look there and you can actually see all of the symmetry elements. So for the more symmetric point groups, you don't actually need to find all of the symmetry elements to be able to see how many they have. But let's talk about what these character tables are. The character table is a complete list of symmetry elements and a set of instructions for systematically describing the symmetry properties of any part of the molecule that you've assigned to that point group. It's a complete list of symmetry elements, okay, and it's a set of instructions for describing all of the symmetry properties of that molecule. These character tables are going to be our tools to describe chirality, to interpret spectroscopy, and describe the function of the molecules that we assign to each point group. And I said that describing the symmetry properties of any part of a molecule, so once you assign the molecule to a point group, any part of that molecule is described in the character table. Some of the parts don't have the full symmetry of the molecule. So for example, if you were looking at the C2V point group, okay, there's a p orbital, on one of the atoms, or a set of p orbitals on all of the atoms that are part of the molecule, but not necessarily described by the total symmetry of the molecule. Everything that's part of the molecule is described by one of the lines in the character table. So the parts here that I'm talking about, it's the fact that many parts of a molecule do not possess the full symmetry of its point group. Examples of these things are, like, for example, a set of p orbitals, or any orbitals, electronic states, and vibrational states. These things directly translate, these electronic states and vibrational states. This is what we use to interpret spectroscopy. Mathematical functions, or in other words, orbitals. So I said set of p orbitals, that would fall into this mathematical functions category. We can also describe sets of ligands. So any part of the molecule, you could pick out pieces of it. It might not possess the full symmetry of the group, but whatever you pick, there is a line in that character table to describe the symmetry of that set, whatever you're looking at. So let's look at the C2V character table. And that's why I gave you the handout. So find the C2V character table. Okay, let's look at this character table. So obviously, you can see that in the top here, this is the point group. And your book calls it a shoe and fly symbol. And I'm not sure if I'm saying it right. It also, as you can see, is a list of all of the symmetry elements. So the symmetry elements are listed here. This number over here, H, is basically all of these symmetry elements added up. So there's one of each kind. So you have a total of 4 different symmetry elements. And so this is H, or the order of the group. And this is useful because if you know what the order of the group is, you can do some mathematical manipulations later on. So order of the group. Let's see, what else do we have here? Well, we have these lines here. The things in the middle, these purple, all of these numbers in here are called characters, and they're the characters of the irreducible representations. Now, an irreducible representation is one of these lines. So just this line, for example, this is one irreducible representation. And I abbreviate that, and I think your text does as well, as IR, but a little r, so that you don't confuse it with IR spectroscopy. So irreducible representations, or IRs, it means you can't reduce it any further. And it's more useful to think of it relative to the reducible representation, which we'll talk about in a minute. So a reducible representation is basically a bunch of those lines added together, and you can pull out the irreducible representations if you know what the reducible is. Symmetry labels are here. I'm going to do that in pink. So all these things here, these are symmetry labels of the irreducible representations. And then over on the right, we've got kind of two columns. The first is transformation properties of vectors along x, y, and z, and rotations around x, y, and z. And the rotations around the different vectors are notated capital R, x, capital R, y, capital R, z. Why is that useful to you? Well, if you want to know the symmetry of a pz orbital, you just look for the z. If you want to know the symmetry of the py or the px, just look for the y and the x, okay? So you can look at these and you can think orbitals when you see them. An s orbital is found over here, where you have the squares of the axes. And so this is the second column, and this is transformation properties of the squares and the binary products of the coordinates, or the axes. Okay, so if you wanted to know what the symmetry of the s orbital was, you look for x squared, y squared, and z squared. Sometimes you'll see something like x squared minus y squared and a z squared in the same line. That's still the s orbital. We'll also be looking for the symmetries of d orbitals. Remember, we have dxy, dyz, dzx, or whatever. They're here. These are the d orbitals that you'll be looking at. Before we move on, I want to talk about the symmetry labels of the irreducible representations, these notations. So the symmetry labels of the irreducible representations are rigorously labeled. So each row of the character table is rigorously labeled. Notice in C2V we have A and B groups. So A and B just designate symmetry with respect to the highest order axis. So if it's an A, it's symmetric with respect to the highest order Cn. Remember that the highest order Cn is the principal axis. And if it's B, that means it's antisymmetric. These two, A and B, are what we call one-dimensional, 1D, or one-dimensional IRs. And what that means, so if I go to C3V, right there, okay, see how this one's not an A or a B? This one has two different things in parentheses. This is saying that these two guys will always transform together. So they have to be together. To have this E symmetry, they need to be together. So that's what we call a two-dimensional irreducible representation, whereas A2 for this one only has one thing. It has Z up here, it has these two guys here, but none of them are in parentheses, so it's saying that so Z, x squared, y squared, and z squared all transform independently as A1, whereas x plus y, or x and y, both transform together with E symmetry. So anytime you have an A or a B, you have one D IRs. What this also means is that under E in the character table, as in your identity, you'll have a number 1. So notice that all of these irreducible representations have a number 1 under E. they must have run out of lots of symbols because they're going to use E again for something different. This is not the identity. This is actually a symmetry label. So E in the character table tells you it's doubly degenerate. And that just means that two orbitals or vectors are transforming together. And that means that you're going to have an E of 2. So the identity operation, if you look at C3V again, notice that under E, so E is the symmetry label, but under the identity, you have a 2 there to tell you it's doubly degenerate. What's your question here? They possess this symmetry as a pair rather than individually. So the X alone would not possess this symmetry. The Y alone would not possess the symmetry, but together they possess the symmetry. Let me go on and see if it answers your question. Okay, so wait, let's do a few more quickly. So T is triply degenerate, and that just means that 3 orbitals transform together. You have a 3 under the identity operation. So A, B, E, and T are the 4 different labels that you can have. They also have subscripts. So if you notice back up here, we had subscripts of 1 and 2. So a subscript of 1 tells you that it's symmetric with respect to a sigma V or a perpendicular C2 axis. 2 is just antisymmetric. So 2 is antisymmetric with respect to sigma V or perpendicular C2. We can also have G or U subscripts, and you've seen these before. G stands for Gerard, and it just means it's even, and this is symmetry with respect to an inversion center. And then there's one more thing that you can have, and that's a prime or a double prime, and that's not technically a subscript, it's a superscript, but I'll write them here as well. So 1 prime tells you that it's symmetric with respect to a sigma H. And a double prime tells you it's antisymmetric with respect to a sigma H. So now let's talk about where the characters come from. What do these things mean? So where do character tables come from? And we're not going to go deep into this, but I'm sure that there are some of you that really like to understand where this comes from, and that's why I'm covering this. I'm never going to test you on this particular aspect, and that is involving matrix algebra. So they actually come from matrix algebra, and if you want to understand this more fully, then I'm going to cover it right now. The Miesler and Tarr textbook in chapter 4 has a nice description, and I've put that online as well. So it's on your blackboard under supplemental reading if you'd like to see it. But in short, every symmetry element can be represented as a transformation matrix over the x, y, and z coordinates. And I'm going to use water as an example. What is the point group of water? Can someone tell me what the point group of water is? What's your principal axis? C2? Does it have a perpendicular C2 axis? Does it have a horizontal mirror plane perpendicular to the primary axis? Does it have a vertical mirror plane? What is it? It is C2V. Okay, so that's the character table we've been looking at. How convenient. All right, there are 4 symmetry operations in the C2V point group, and let's look at them. So E, C2, sigma V, XZ, and sigma V, YZ. And I put my coordinate system here so that I can follow it. It doesn't matter how you define your coordinate system, but it's convenient to use Z as the principal axis, and it's important that whatever coordinate system you use it consistently throughout the entire problem here. So I wouldn't want to switch X and Y while I'm looking at this particular molecule. So let's look at E. And a transformation matrix, you may or may not be familiar with this, but we have the X, Y, and Z coordinates. Basically what we're going to say is that after the operation, I'm going to say X, Y, and Z prime, which would be after the operation, is going to be equal to the original coordinates times, a transformation. Okay, and I could say that for all of them. So it turns out that our the transformation matrices need to be 3 by 3, and basically what we're going to do is look at what happens to X, Y, and Z, and then the other guys end up being 0. Okay, so that's what we're going to do when we're doing this. So each one of these can be represented as a transformation matrix. So these are the transformation matrices of the 4 symmetry elements. I'm going to erase that little X, Y, Z. You're going to assign characters. Remember this? X. Little character, and it's going to depend on what happens. So if no change happens, and we're going to look at the 3 vectors. If no change happens, you're going to assign the vector a 1. If the sign of the vector changes, and only the sign of the vector changes, it's assigned a -1. And if there's a more complicated move, you just assign it a 0. During the E operation, which is doing nothing, what happens to the X? It doesn't move, right? So you assign it a 1. So that's going to be a 1 there. Y doesn't move, assign it a 1. And Z doesn't move, you assign it a 1. That's a transformation matrix of E. Now, for C2, what happens to X when you rotate 180 degrees? It sure does. So it goes into the negative of itself, and so that's sign changes only. So that is a -1 for X. What about Y? What happens to Y when you rotate around Z? 180 degrees. It's a -1. What happens to Z when you rotate around Z? 1. Yeah. Okay. How about sigma V X Z? So we have to remember how we're defining this. So XZ is basically the plane of the paper. So if you reflect through the plane of the paper, what happens to X? So the plane of the paper, so you basically just reflect through the plane of the molecule. And I'm talking about the plane of the paper as I draw this, yeah. Okay? So what happens to Y? It's reflected to the opposite side. Okay, so it would be a -1. Yep. Y is the only thing that moves. Okay? And then for the other reflection plane, yeah, X is the only one that's reflected, so Z and Y stay the same. So it would be -1, 0, 0, 0, 1, 0, 0, 0, 1. So those are the transformation matrices. This is what gives you the character tables. So this essentially is a character table. I can get 3 out of the 4 irreducible representations. So notice in a C2V there are 4 irreducible representations. 3 of them come directly from this matrix. So I'm going to kind of draw the character table down. I'm going to circle all of my X coordinates here, okay? Let's look up at that character table. Where's X? Here's X down here. Yeah, the B1. Let's see if that looks the same. So E, the irreducible representation for X is 1, -1, 1, -1. Does that match up with X in your character table? That's what we mean by that the X vector transforms as B1. Now let's look at Y. I'm circling all my Y coordinates in blue. So this would give me 1, -1, -1, 1. Is that the same as Y in your character table? Okay, that's what we mean when we say the Y or the PY orbital will transform as that symmetry. The Y vector or anything with the symmetry around Y will transform as that. And what is the symmetry label for that one? Okay, and then let's look at Z. Now, we defined the Z-axis as the one that was the principal axis, right? 1, 1, 1, 1. And I imagine that that's A1 symmetry because it's one-dimensional and it's symmetric with respect to that principal axis because of the way I defined it. So if you define your axes with the Z as the principal axis, you will always have Z transforming as A1. So if you added these up, this would be 3, negative 1, 1, 1. And this is what a reducible representation looks like. And it's represented by this little thing that looks like a hangman. Again, this is a Greek symbol. But you can add up the IRs, or the irreducible representations, to give a reducible representation. And we don't usually add up the IRs to get a reducible. It's more common for you to find a reducible representation and then to break it down into its irreducible representations. So I know that I have not found all my irreducible representations because of two things. The number of IRs equals the number of classes. What are the number of classes? Those are just the number of columns in the character table. So I have 4 different columns here. I need to have 4 different irreducible representations. The other way I can know this is that the squares, so basically the sum of E2 squared, the sum of the E2 squares has to equal the order of the group. So 1 squared plus 1 squared plus 1 squared does not equal 4. How do I find the last irreducible representation? Well, all of the characters under sigma v prime should add to 0. All of the characters under sigma v should add to 0. All of the characters under C2 should add to 0. And basically you add the squares of these guys up, and they should equal the order of the group. So by inspection, I can just say that my last irreducible representation is going to be 1, 1, negative 1, negative 1. And that would be my A2. You'll never have to find the irreducible representation because you can find it with the character table, as long as you can assign the point group. I'm only telling you this so that you understand where these come from. Okay, so now we know a little bit more about symmetry elements, point groups, and character tables. Remember why we were doing this in the first place? We started this whole thing because we wanted to know how to make molecular orbital diagrams. And we said there were 2 ways to do it. We could guess about what pendant ligands looked like the SALCS, or we could actually do it systematically. And I said, well, before we do it systematically, we need to understand symmetry and character tables and point groups. So, now that we know about symmetry and point groups, let's use what we've learned to systematically draw the molecular orbital diagram for water. And I'd like to point out that another sheet that I gave you just now is entitled SALCS. And this is a how-to guide that will help you get through this. I will number my notes just as I've numbered that sheet. I will have a little bit of a different explanation in my notes than is in the sheet, but I'm hoping that will help you get through this stuff. There's a lot of stuff here, so don't be surprised if you go through this the first time saying, what the heck is going on? The 3rd or 4th time, it'll start becoming really systematic, and you'll be able to see what's going on. So I'm going to go through this step by step. The first step is to find the point group of the molecule. And we've already done that for water. I'm going to draw my molecule. I'm going to define my axes. And we already said that it's C2V. Second step is for pendant ligands, you need to identify which orbital sets are going to interact with the central atom. So on water, what are your pendant ligands? These 2 guys, right? Hydrogens are your pendant ligands. What are the orbitals on hydrogen that are interacting with oxygen? What is the only orbital available on hydrogen? Yeah, it's an s orbital. That won't always be the case. Sometimes you'll have pendant ligands that have p orbitals as well. And so you'll have to take care of all of those. But for now, we're just dealing with s. I care about the number of orbitals I start with because I need to know how many SALCS to expect. Remember, the SALCS are sets of pendant ligand orbitals. Symmetry adapted linear combinations of these pendant ligands. So for our purpose, for this water molecule, we have 2 hydrogen 1s orbitals, and that should give us 2 SALCS. You always have the same number of SALCS as you do of contributing orbitals when you start. So we found our point group, we expect 2 SALCS, and then the third step is to generate a reducible representation. So this is what we were talking about back up here, this reducible representation. This is one reducible representation. We're going to find the one for the 2 different hydrogen orbitals SALCS. So I'm going to draw a little picture where my oxygen atom is just going to be a dot. And then here we've got our 2 different hydrogens, H1 and H2. What we're going to do with a reducible representation, in order to generate a reducible representation, we are going to do all of the operations in the C2V point group, and then we're going to assign characters to each hydrogen 1s orbital. So in other words, we're going to assign characters to each hydrogen 1s orbital for each operation in C2V. What are the characters going to be? We're going to assign a number 1 if the hydrogen doesn't move. We could assign a negative 1 if you moved a hydrogen into the negative of itself, but since the s orbitals only have spherical positive sign, that's not possible, so I'm not even going to write it down. The last option is to assign a 0 if hydrogen moves. So if it's moved away from itself, then it's got a 0. So let's write down C2V symmetry operations. E, C2, sigma V, XZ, and sigma V prime, YZ. So for each hydrogen orbital, we're going to assign a number 1, and we're going to add them up if it doesn't move. If it moves, each one gets a 0. So for C2V, so this is going to be my reducible representation right here for hydrogen 1 and hydrogen 2. How many of those hydrogens move during the E operation? How many move? Nothing, right? So each one of the hydrogens gets a number 1. You add them together, and your reducible representation under E is a 2. For C2, you rotate around the V axis. What is the character here going to be? It's going to be a 0. For sigma V, we're going through the XZ plane. The coordinates are, the coordinate system is up here. The XZ plane is the one in the plane of the page. Or what's the character under this sigma V? They both stay the same.
Yes.
So it's a 2. What about for sigma V prime? Teresa, what do you think? Sigma V prime, it chops the molecule in half, perpendicular to the plane of the page. You do add it together, but what's the character for each one?
Oh, for each one, 0.
Yeah, so 0 plus 0. So this one's 0. Yeah. Now we've got our reducible representation. Next step, I'm going to write this in a different color pen because you'll see why. The next step is to generate irreducible representations, or in other words, break that reducible representation into the IRs. There's 2 ways to do this. I like to just use the rule that, well, I can just do this by inspection. So I can see that this is going to break down into 2 different IRs because each of the IRs is actually going to be one of my SALCS. So I'm going to need 2 different IRs. For all of my E characters, it's always going to be 1. So I need 2 different IRs that have 1 as a character here. I need one that has a -1 and a 1 to add up to 0. This is going to have to be 1 and 1. And this is going to have to be -1 and 1. A1 and B1. Yeah. That's a good question. So I actually think it's because I have experience and I know that the A1 is it's usually always a part of it. There's a systematic way to do this, and I'll show you. But I think it would actually work out if you had the other. If you switch those, I think it would still work out. We should test that. So once you get the irreducible representations, you can actually stop. And you can make your molecular orbital diagram because all you need to know is what the symmetry of the 2 SALCS are. I know now that my symmetry, the symmetry of the 2 SALCS is A1 and B1. And that means that anything with those symmetries are going to line up and match with this. So if I wanted to know which oxygen orbitals were going to combine with my SALCS, I could go to my C2V point group character table. What did I say I had? A1 and B1. So my oxygen atomic orbitals that are going to combine with A1 are Z and S. B1 is going to combine with X, and it would also combine with the D orbital, D's XZ, but that doesn't exist on, oxygen doesn't have a D orbital, so I don't have to worry about it. So I know now that when I draw my molecular orbital diagram, I am going to combine the SALC with A1 symmetry as Z and S, and I'm going to combine the one with B1 symmetry with the PX orbital. So if your only goal is to draw the molecular orbital diagram, you can stop here and draw molecular orbital diagram. I just wrote something here. We can stop here and draw molecular orbital diagrams by matching up oxygen orbitals that have B1 and A1 symmetry. Notice that I drew the B1 and A1 with lowercase letters. When we're talking about irreducible representations, you use capital letters. When you're talking about orbitals and SALCS, you draw lowercase letters. So anytime I draw a molecular orbital diagram and I'm labeling my orbitals or my SALCS, always use the lowercase letters that match the symmetry labels for the irreducible representations. Just a little notation thing. Now, we're not going to stop here because there's more steps if you want to know what the SALCS look like. So, if we want to know what the SALCS look like, we can go on. And sometimes you will be asked to draw a SALC. So then you go on to step 5. And step 5 is to use the orbitals on oxygen, and I call them generator orbitals, with A1 and B1 symmetry to actually make the SALCS. And again, this is the same as guessing. This is the same as our guessing thing that we did before. So we know that the A1 orbitals have S and PZ symmetry, and the B1 orbitals have PX symmetry. So I'm going to draw the S and the PZ orbital here, and my SALC, I'm going to draw an orange, would have 2 of the hydrogen 1s orbitals of the same sign. So this is one SALC, I just drew it twice. And then the PX orbital is like this, and our SALC now has a node because the two signs of the s orbitals are opposite. So this is the px, pz, and s orbitals. And that would be our two SALCS. Now, if you don't want to guess, there's a systematic way to do it. The way you do it systematically is you generate something that's kind of like a reducible representation, but it's not exactly. What we're going to do here is we're going to follow one of the ligand's positions in all operations. So I'm going to follow H1. And I'm going to assign characters. So these are like my fake characters, but they're analogous to characters. You're going to call it H1 if H1 doesn't move. And in this case, there's only one other option. If H1 is moved into H2, you call it H2. So if you had a lot of different ligands, you would just call it whatever ligand it's moved into. Let's write our character table here. So C2V character table. I have my E, my C2, my sigma V X, Y, and my sigma V prime. Sigma V prime. YZ. Okay, so what happens to H1 under E? It stays H1. What happens to H1 under C2? It's H2. What happens to it under sigma V in the plane of the paper? H1. Sigma V, chopping the molecule in half. H2. Okay, there we go. Now, what you do here, you take this guy, now I'm going to call this number 7, and you multiply the values from the two irreducible representations from step 4. I think I wrote that in blue, right? Yeah. So I'm going to multiply the values from the irreducible representation from step 4 with the table you just found above. And then you add them together to make a linear combination. Let me show you. So I'm going to redraw my character table down here again. Okay. And I'm going to take, I said that I had an A1 IR here. Okay, so we have A1. A1's irreducible representation is 1, 1, 1, and 1. So now I'm just going to multiply that by this guy up here. So I'm going to say 1 times H1. C2 is H2. V is H1. This one's H2. And if I multiply that and add them together, I will get 2 H1s plus 2 H2s. Think about adding wave functions together. When you have two wave functions, and you can think of the H1 and the H2 as two different wave functions, when you have two wave functions of the same sign, and you have two things with the same sign, this is going to look, this is the SALC that looks like this guy up here, okay? How do we know? So you have an A1 SALC, both of the lobes, or both of the hydrogens are in phase, and each orbital has equal amplitude, and you can tell that because they have the same number out front. So your A1 SALC is in phase, and each orbital has equal amplitude. So I have H1 and H2. This is my A1 SALC. Let's do the same for the other irreducible representation we found. So it was B1, right? So B1 is 1, -1, 1, -1. What does that SALC look like? What's the linear combination? Good, 2H1 minus 2H2. So, can you see now that these two orbitals, this is going to be a SALC that's out of phase, and each orbital has the same amplitude. So this is the B1 SALC, it is out of phase, and each orbital has equal amplitude. This is H1 and H2. And then step 8 is to draw your molecular orbital diagram. So this one is going to look very similar to what we drew before. So if you go back in your notes, these two guys should match. I'm going to zoom out a little bit. So I'm going to draw the molecular orbital diagram for water. I'm going to draw my oxygen atomic orbitals on the left. Doesn't matter if you draw them on the left or the right. So the atomic orbitals I'm dealing with are going to be the s orbital and the 3 p orbitals. Okay, and remember what these look like. Pz is this one, py is that guy, and px that guy. Now, what are the symmetry labels that I need to put on these orbitals now? What's the symmetry of S? Look at your C2V point group. Look at the character table under C2V. How do you know what S is? Yeah, it's x squared, y squared, and z squared all on the same line. So what's the symmetry? It's A1? Yeah. So A1. What is PX? B1. PY? B2. And PZ? A1, yeah. Okay. And then we can draw our hydrogen SALCS on this side. So there's our two SALCS. What's the symmetry labels that we put on these? What's the one on the bottom? A1. And then the other one is B1. Why did I put B1 higher in energy than A1? What? Yeah, because it has a node. So always put your orbitals that have, or the SALCS that have nodes, higher in energy than ones that don't. The more nodes, the higher the energy. Okay, so now how many A1 orbitals do I have that are going to combine? Total.
3.
3 total. So I should have 3 molecular orbitals in the middle that have A1 symmetry at the end. So the oxygen s orbital and the A1 SALC are going to combine, but they're not going to combine as well as it's going to combine with the PZ. So there's a slight bonding interaction there. The A1 PZ and the A1 SALC are going to combine to give you a bonding interaction because they're closer in energy level, and so they're going to have more favorable interaction. And then you're going to have an antibonding orbital. Technically, you can say that this A1 s orbital is contributing to all of the other guys as well. Because technically it has the symmetry to do that. But you should know, don't care if you draw the lines or not, you need to know that the A1 is going to be contributing most to this, the s orbital is going to be contributing most to this mostly non-bonding orbital, and least to the antibonding orbital on the top. So here I'm going to label these A1, A1, and A1 star. If you wanted to draw what they would look like, the A1 would have the most S character from oxygen. The second A1 would have the most PZ character as far as the oxygen orbitals go. And the A1 star would also look more like the PZ than it would the S orbital from oxygen. Does that make sense? Why I'm drawing? So I could draw the S orbital up here like this, and there's certainly some degree of S character in that antibonding orbital, but it's going to be mostly PZ because it's closer to the PZ energy level. Capiche? Okay. All right. So then let's do B1. So we have 3 A1 molecular orbitals. We started with 3 A1 atomic orbitals. We're good. How about B1? We are starting with how many? 1 here and 1 over here. There's 2. So we'll get 2 molecular orbitals. The B1 SALC is going to combine with the B1 px orbital, where will that energy be? Above or below my bonding A1 here? Yeah, it'll be above. How do you know that? Yeah, I actually think the easiest way to do it is look at the fact that B1 is higher in energy than A1. All of the p orbitals are equal in energy. So if you combine two orbitals, so if you combine this orbital with the p orbitals, it'll be lower in energy than if you combine this orbital with the p orbital. That's a guess. We wouldn't really know unless we did some spectroscopy. That's a pretty good guess. So I'm going to try to put my B1 bonding orbital there. And then where should I put my B1 star? Should I put it above A1 or below A1? That's a good guess. I would say put it below. But you don't know. You really don't know. So the reason that I would say put it below is because I think you would want to fill that less stable antibonding than you would knock out the B1 bond first because the B1 bond is higher in energy, but you don't know. So you could draw it there or you could draw it up here. I don't know where it is, and neither do you. So all you can do is use reasoning to guess. And if you can give me a good reason, then that's good enough. Okay, and then we have one more thing to look at, and that's the B2. And this B2 is not bonding with anybody. I'm going to go back and I'm going to draw what the B1 bond, the orbitals look like. So this would be my PX with my SALC. And then this one would be PX with the SALC. Fill in electrons. There's 2 electrons from hydrogen, 6 from oxygen, so that's 8 total. What I want you to do before you come back here on Wednesday is I want you to try to construct a molecular orbital diagram and pictures of the SALCS for BH3. So go through steps 5, 6, and 7 here. So these 5, 6, and 7 are really just what does SALCS look like. So next time we're going to look at BH3. There is a more systematic way to find the irreducible representations, and you can look for that in your textbook. It's also in the Meets Learn Tar textbook, and I will cover it next time because you may need it for BH3, and if you don't need it for BH3, you will eventually need it in your life. And then we're going to talk about applications of symmetry. We're going to start with vibrational spectroscopy. Have a good Monday. Have fun at the ACS.